So, let us look at a generalized flow in quasi 1D, which consists of a combination of various parameters like variations in area, variation, there may be friction, there can be heat transfer. There is also an additional factor which we had not accounted till now, is if there is an injection of mass, if mass is getting added. Also this, which is typical in cases of say propulsion systems where there is some fuel getting injected into the flow, then there is a mass addition also happening. So, we will look at these cases. Until now the analysis we were doing used quasi 1D assumption, which is that flow properties remain uniform across cross sections, and we looked at different drivers, like either only area was changing, or there was only friction and no other effects were there, it was a constant area duct. Similarly, only heat addition or heat removal. But in real life problems and applications, there is always combination of these effects. So, how do we analyze such flows? Before we go there, we will just quickly look at what happens when there is mass addition without going much into details, because now this process of doing a quasi 1D analysis with a control volume must have become quite familiar, and this can be now you can do this continuously. So, now if you look at this, what is this simple control volume that is taken? You have a constant area duct, and at some place the mass is getting added, certain dm dot is getting added. So, across this control volume there is a increase in mass. So, m dot is not a constant anymore. So, not a constant, there is a variation of m dot, and you can get the differential equation from this quantity, this d m dot by m dot. Rho a v is the mass flow rate through a particular cross section, that is m dot. So, d m dot by m dot can happen due to changes in density, change in area, and change in velocity. So, there can be domain. If you consider a constant area duct, then dA by dA is 0. So, d rho by rho plus dV by dV. So, changes in mass flow rate will get affected in terms of change in velocity and density. And if you consider the energy equation, here we are considering that this particular mass that is getting added is having the same stagnation enthalpy as the main flow. So, both of them have same stagnation enthalpy, therefore, there is no change in stagnation enthalpy when additional mass is getting added. That is the assumption being done here. In general, this can be different, we will soon see that one also. So, h plus v square by 2 is a constant. So, you can write now in terms of derivatives. Now, if you look at the momentum equation, you should be careful here, because in general this mass that is getting added can have a velocity which can be in any general direction, need not be along the same axis. So, it need not be along the same axis. So, we are looking at only 1D flow. So, we are looking only along x axis. Therefore, we should take the component of velocity in the x axis, which is u here, to look at momentum equation, x momentum equation. Solve that. So, P A minus P plus dPA, this is the pressure force, is equal to change in momentum flux, which is m dot plus d m dot v plus dv minus m dot v minus d m dot u. Now, this u by v, the component of the force in the direction, in x direction for the injected flow, u by v, that is given the term theta, it is a parameter in this problem. Okay. So now you can divide the entire equation by m dot, and this equation can be got from here. Now as we did in all other cases, our intention is to represent the main governing equation. Here it is a momentum equation. You express momentum equation solely in terms of Mach number. This can be done by series of algebraic manipulations of the different equations, which is how pressure is related to the equation of state P is equal to rho r T, okay, and d rho by rho plus dt by t, okay. Then you have Mach number is V by A. How is that related? Then you have P naught by P, this relation. From here you can get the relationship between P naught and P, and similarly the impulse function, and also you consider the dt naught, okay. So you can plug all of them, and then look at integrating this with dm dot by m dot as the driving parameter, and similar to all other cases you can also have the star point, which is the reference point, and you can get closed form solutions for mass addition also. So let us directly go and look at how mass flow mass addition affects various parameters when it is when the flow is subsonic. Similar to all other cases, when flow is subsonic, Mach number increases, velocity increases, pressure, temperature, density decreases, and entropy always increases. So mass addition, entropy increases. There is but in supersonic flow it goes the other way around, which is Mach number decreases, pressure, temperature, density they increase, and velocity decreases, again entropy will increase. So that is a quick introduction that we did not consider mass addition, but mass addition is also can be a possibility in specific applications. So just before we go to the generalized case, where we consider all possible variations of the driving forces or drivers of these equations, this was a quick introduction to mass addition. The general analysis tools are similar to what we had done for the previous cases. So now let us look at the generalized steady 1D flow, where you can have all kinds of effects that is happening. One is that it is a varying area duct, so area change is happening. Then we are considering that there is wall friction, so there is a frictional force along the walls, so friction is considered. There is heat that is getting added or removed, so heat transfer is there. External work can be done or done by the system or on the system. There can be mass addition with different sort of temperature, stagnation temperatures and pressures for the mass being added. You can have body forces, and also in some cases you can have some entrained particles which induce some drag. So another drag force is also present, and there can be effects like there can be chemical reactions which can change properties of the fluid, that can also be considered. For the case that we are discussing here, we will still consider calorically perfect gas. If chemical reactions are happening, that assumption is not completely right, but for the sake of a analysis in this class, we will just consider the calorically perfect gas. So what do we do now? We write the conservation equations, now considering all effects. So now you have m dot is rho AV, and therefore area is also changing. So you have dm dot by m dot is d rho by rho plus dA by A plus dV by V. Now, momentum equation you can consider, you have all the various parameters dP, rho v dV is the momentum flux, and then the body force term rho g dz, then the frictional force term rho v square by 2 4f dx by d. How we reached at each individual part of these terms we have already discussed in those corresponding sections. How we got this was dealt with in Fanoff law. Similarly, this is delta D by a reference, so force by area, so that it is consistent in dimensions where D is the drag force, and this particular quantity rho v square multiplied by 1 minus y dm by m dot, where y is the same as theta, which is u by v. We have just now discussed in this particular section. So, this is due to mass addition. Similarly, if you like to take a look at the energy equation, again you come to work done, heat added or removed, and then here is the change in total enthalpy of the is a difference between what is outgoing and what is incoming. Okay. So, outgoing is given here h plus dh v square by 2 plus dv square by 2 plus gz plus dz, while incoming is one is due to the core mass flow, the other one is due to an injection dm dot, and here it can have different total enthalpy which is for the injectant. Okay. So, that is possible. Now, in this energy equation you can combine different differentials together, and here is the change in h naught, it is d h naught, this entire term d h naught, while this is due to heat due to the mass addition term, which is also a change in h naught for the mass addition d h naught I. Okay. So, d h naught I. So, finally, this is the term here which comes out, which is nothing but the statement that work done and heat added or removed will be changing the total enthalpy of the system. So, here the parameters are the driving parameter here is a combination in the energy equation, it is a combination of heat that is added, work that is taken out, shaft work, and also the work or the total difference between total enthalpies of the injectant fluid and that of the main fluid, and if you divide that entire equation by Cpt. So, this is a driving force or driver of the equations, that is related to change in stagnation temperature. Similarly, we can write down for momentum equation, you can write down in terms of dP by P, dm by m, dt by t, and so on. Here you have, of course, this part is dm dot by m dot. Okay. So, and the definitions of this comes from P is equal to rho RT. So, dP by P is d rho by rho plus dt by t, and Mach number is defined as V by A, and A goes as square root of t, that from there dm by m is equal to dV by V minus 1 by 2 dt by t. Then you can use T naught definition is T multiplied by minus 1 by 2 m square, and from there you get this equation. Similarly, P naught. Similarly, the definition of impulse function f is equal to 1 plus gamma m square multiplied by P A, okay, and the definition of entropy. Okay. So, you get all these different equations. So, all of them can be taken together. So, what are the unknowns? Pressures, density, temperature, velocity, Mach number, stagnation pressure, impulse function, and entropy. And what are the various driving changes that drive these different parameters. They are mass addition, change in area. This K plus L is due to drag forces. So, that is momentum equation. In the momentum equation you have friction, drag and momentum deficit due to mass addition. So, that is over here, and dt naught by T naught, which is change in stagnation temperature, and of course, dA by A is just the change in area. So, each of those equations can be written in a matrix form. For example, dP by P is equal to d rho by rho plus dt by T. This can be expressed in completely matrix form over here. Okay. So, that can be done if you do the proper multiplications here, then you will find that equation. Similarly, if you take the first equation, which is the mass flow equation, which was d rho by rho plus dV by V is equal to dm dot by m dot minus dA by A. This is from the mass conservation equation that we have done over here from this equation, and that equation can be found by doing the multiplication of the first row with this column corresponds to the first value over here. So, this complete equation, basic matrix equation, basically represents the set of all equations that we have considered. Now, this can be inverted. So, the way to solve this is you have to express each parameter dP by P, d rho by rho, dt by T in terms of these driving potentials, these driving potential and a influence coefficient associated with them. This can be solved analytically. You can use, nowadays there are good analytical solvers like Maple, Mathematica, even in MATLAB it is possible. You can represent dm by m using Kramer's rule. You can represent all these different flow property to a driving potential, which is changes in area due to friction, due to heat processes, which is change in stagnation temperature and mass addition. So, if you consider say dm by m, how does Mach number change? It has an influence coefficient associated with it for a driving potential dA by A. Along with that, plus an influence coefficient due to frictional forces multiplied by this quantity, plus an influence coefficient due to dt naught by T naught multiplied by T naught. So, for every flow parameter we can, flow property, we can write this influence coefficient for that corresponding driving potential. So, it is possible to do it, and therefore, we can write, for example, if you consider dm by m. So, for this you can write down the entire solution, which is, it is 1 plus gamma minus 1 by 2. Okay. It is 1 plus gamma minus 1 by 2 m square by 1 minus m square, and you have the term associated by dA by A, and you have the term associated with friction, you also have term associated with drag and dt naught by T naught and mass addition also. So, this considers all the different properties. And how is T naught related to T naught 2 related to T naught 1? It is related by the energy equation, where you can consider heat work done, heat added, work done by the system, and this is the difference between injectant mass, total enthalpy, and the enthalpy of the main flow. So, if you consider mass flow rate is nothing but rho a v. If you consider two particular points, or at a particular point you can relate it to pressure Mach number. This was done in previous classes. From here we can get to P2 by P1, and since there is an injection of mass also available, m2 and m1 need not be the same, that should be understood over here. So, if you can solve for say Mach number, and to do that you have to integrate this can be integrated using any numerical tool, there is no analytical way this can be done. But some qualitative aspects of how we can know what is happening can be understood by just clubbing all of them together into a particular function lambda. Before we go there, the way to solve these problems is write down any parameter. For example, here we have written it in Mach number dm by m can be written as a function of all the driving potentials and Mach number, and we take 2 points 1 and 2. We should know the initial condition at 1, and it can be integrated to 2. Okay. It can be integrated to 2. You can use any numerical integration algorithm. Once you know properties at 1 and 2, m1 and m2, then all other parameters can be done. So, we can club all this together, the entire thing can be clubbed together as lambda. Okay. So, this complete expression is lambda. Lambda now has influence of all various parameters. So, now if you see that your dm by m is lambda by 1 minus m square. Okay. So, we can look at what will happen if lambda has different signs, similar to what we were looking for, say area change or friction or heat addition separately. Then what will happen to this particular value. So, if you take lambda, it can have initially it can have negative sign, or it can have positive sign, or it can be 0. Okay. So, you have this equation dm by m is equal to lambda by 1 minus m square. So, depending on the sign of lambda, you have various descriptions of the flow. So, initially suppose we take that lambda is negative, and you consider that lambda is less than 0, and here you have in x direction. So, this is the flow that is varying along x, quasi 1D flow, and on y axis it is Mach number. So, if you begin with say a subsonic Mach number, that is Mach number is less than 1, and that lambda is negative. So, lambda is negative. If lambda is negative, so lambda by 1 minus m square, m is less than 1. So, this quantity is going to be positive. So, dm by m will be negative, that means Mach number will continue to reduce. So, this is the direction of how the flow would vary. With lambda being 0, there is no change in Mach number, that is a critical point over here. But if lambda is initially negative, a subsonic flow continues to reduce, supersonic flow will continue to increase, because this becomes negative, and the lambda is negative, negative by negative is positive. Initially, if lambda is positive, then the directions reverse, and initially subsonic flow will accelerate, you will have increase in Mach number to 0.1. Similarly, you have a supersonic flow, its Mach number will reduce. But what if lambda switches sign in between? So, that can happen. Lambda can be initially negative, it can switch sign at some point, become equal to 0, and then the sign can change and it can become positive. So, if you consider such an effect, then initially if lambda is negative, a subsonic flow will decelerate, then lambda will become 0, and after that it will accelerate again. Okay. Similarly, a supersonic flow first will accelerate, it will increase Mach number, lambda will become 0 and then it will decelerate. So if it had started from 1, it accelerates, decelerates and comes back to 1. But if you consider a case where you have initially lambda is positive, then a subsonic flow will accelerate, then it will reach lambda equal to 0, which is a critical point when Mach number is 1, and then further it can increase when lambda switches sign and lambda becomes less than 0. All the cases of variable area ducts must remind you of this kind of an approach. From a initial subsonic case, it goes to supersonic flow, or from an initial supersonic flow it goes to a subsonic flow. If you are not achieving the critical point, which is lambda equal to 0 at Mach number equal to 1, then you will just increase in a subsonic flow. First it will increase, then achieve the maximum point, then again it will decrease. Similarly for supersonic flow, first it will decrease, achieve a minimum point and then increase the Mach number. So you can see that these different curves for different cases of lambda have the elements of various aspects that we have already discussed separately in different cases, whether it be variable area ducts or it be Fano flow or Rayleigh flow. When you have combinations of them, you have to look at lambda where you have a complete combination. For example, if we consider a case consisting only of friction and area change, which can be a flow through a nozzle converging divergent passage with friction, then what you will see, all other drag and change, there is no heat addition or mass addition, then you have a term here minus dA by A plus gamma m square by 2 4 f dx by d. If there was no friction at all, then it is only due to changes in area, and we know that the critical point occurs at the minimum area, which is at the throat. But if there is friction also added along with that, then critical point should occur when lambda is equal to 0. But when lambda is equal to 0, so if you get the minimum point is dA equal to 0, that is at the throat, but still if you consider friction, 4 f dx by d is greater than 0. So lambda remains greater than 0, so lambda remains positive. So a Mach number should be still, it should be subsonic. So lambda equal to 0 achieved at m equal to 1, that is the critical point, and this you will be able to achieve when dA by A is exactly equal to gamma m square by 2 4 f dx by d. Now this term is greater than 0, that means dA by A should be greater than 0. That means the choking, when you consider a both area and friction, choking will happen in the divergent passage slightly downstream of the throat. Okay, so this can be this is a result that comes out of considering multiple parameters. Similarly, we can consider heat addition or mass addition. So the idea here was to introduce the topic of generalized quasi 1D and show that you can actually do the generalized solution where different driving potentials can be considered together, and we can look at solutions of them. These are useful for doing initial engineering calculations before going on to more say CFD kind of approach or an experimental kind of approach. You want to quickly know what will happen when you have both friction, heat addition and area change happening, which is typical to say propulsion devices or nozzles or diffusers in real flows. An idea of how they would behave can be understood with the help of this generalized 1D flow, and further studies can be carried out later by using CFD approaches or experiments. So with this we come to the close of discussion of quasi 1D kind of approach. It's we have had a very elaborate discussions on this approach, and they provide you the basic understanding of gas dynamic flows, which is important. But when we are considering more practical problems, we want to know what is happening to the flow field, what are the details of flow structures and so on. For that we have to use the differential equations, and one particular way is looking at the first we always look an approach towards the inviscid flow. So, that is what we will be dealing from the next class onwards. In this particular course we will not go into high fidelity models like CFD or and so on, but people have been looking at approximate methods, potential flows and such approaches. We will look at them and see what are the important results that come from such an approach in the coming classes. So, there we will be looking at complete flow field instead of such approximation that flow is uniform across a particular cross section. So, with that we end the quasi 1D discussions. Thank you.